Okay, so the division algorithm. Basically, I put both that in the original a equals qb plus r and a equals qc plus r for the extended one. It won't really apply to this, but just thought the rainbows. But the only difference is that b, in the b one was b is positive. Well, this one, c can be negative or positive, it just can't be 0. Besides that, they're all integers here, and this is basically division with remainders, essentially. Like, it's pretty much what it is, especially the first problem. So for each of the following choices of a and b, find the quotient q and the remainder r in the division of a by b. So a divided by b is 203, it's a equals 203, b equals 17 here. First we divide and get the decimal form, then we take the guess of q equals 11, because it's, we're going to be adding on the remainder in the end. So might as well aim so that 11 times 17 will be a little bit less than 203. So we go on to rounding down instead of rounding up like we normally would under rounding, but rounding down. And basically r equals, a minus qb. So plugging out what do we know, a, b, and us q. A, q, and b. And we get 16, so q equals 11 and r equals 16. A equals negative 203, b equals 17. We divide, but we get negative 11.94, it's about. So let's just try q equals negative 11, r equals negative 203, minus negative 11 times 17. We eventually get negative 16, but the restriction always is that r is greater than or equal to 0. That is what we're doing. So we cannot use this. So we'll let q equals negative 12, which is common in this type. So with negative like this, when a is negative like that, essentially you probably want to do you do round down technically when you think about it. It's to a lower number, because negative 12 is smaller than negative 11.94, even though it's, so basically, yeah. But point is that we do get, with q equals negative 12, we get a remainder of positive 1 as shown here. So q equals negative 12, r equals 1. A equals 0, b equals 17. Well, we know 0 divided by 17 will equal 0, which is already an integer. So we have perfect division, here. We have no remainder division. So q equals 0 and r equals 0. We can even check it when we know q is equal to 0. There's like no possibility, no rounding unit. It would be 0 minus 0, which is equal to 0. So r is equal to 0 and q equals 0. If q was something else but we have no remainder, it would also work out, so you could still calculate. But still. Like 4 divided by 2, for instance, would be 2, remainder 0. And you'd basically have 4 minus 2 times 2, which is equal to 0. But that's beside the point. I think that's a simple concept. But now number 5, this question here. Does n congruent to 0 modulo 5 mean the same thing as 5 divides n? And the answer is yes, because the theorem shows it. It's basically it's basically using the theorem verbatim. A congruent c modulo m is equivalent to m divides a minus c. So n is a and 0 is c here, and modulo 5 is modulo m. So we have 5, 5 is m. So this is equivalent, the expression given here is equivalent to 5 divides n minus 0, which is equal to 5 divides n. Yeah. So for this problem, we have a and b. If a and c are both in 3z, must they have the same parity? So part A is like this. So the answer is no, and we show this by a equals 3 times x is in z, and we plug in for this. Basically, we do just 1, we're trying to find a counterexample, so we have 3, which is odd. B equals 3y, y is in z. b equals 3 times b equals 6, which is even. So odd, even, they can't have the same parity. They have to have be both odd or both even. If a and c are both in 1 plus 6z, must they have the same parity? Well, 1 plus 6z means that a equals 1 plus 6x, which is equal to 1 plus 2 times 3x, x and z. And the same with y. C is in 1 plus 6z, implies that c equals 1 plus 6y. So that's 1 plus 2 times 3y. These are both the definition an odd number. Like an even number is 2 times a number. An odd number is 1 added to 2 times a number. 1 plus 2 times a number. Regardless of what 3x and 3y are, you know, whatever, if any integer basically, it'll work out that times 2 plus 1 will be odd. You can do this for a million, trillion integers, million or trillion integers, and it'll stay the same. So both a, c are odd, so they have same parity. And this question has two parts. First part, write 88 in all possible ways as a product CD of positive integers with the same parity. So positive divisor of 88. So we need the same parity, so we only have 2, 4, and 44, and 4, and 22. 1 times 88, 1 is odd, 88 is even. 8 times 11, 8 is even, 11 is odd, but 2 times 44 are both even, and 4 times 22 both are even. That's part 1, just finding the divisors that have the same parity. Find all solutions of the equation x squared minus y squared equals 88 in positive integers x and y. So positive integers x and y, in effect, that's x squared minus y squared, makes this somewhat simple. I'll let you know what you're doing. So we can write this as x minus y times x plus y by factoring is equal to 88. And so x minus y will always be less than x plus y. You can show this, or you can just logically say, yeah, that makes sense if you don't. Because basically if you add y and subtract x, you'll get 0 is less than 2y. So that hopefully makes sense. And the fact that x minus y and x plus y have the same parity is also important, because if they both have the same parities and we only have those two factors to multiply, you know, we only have the fact that both of them have to have the same parity, so there's only there's only two possibilities really for what x minus y and x plus y can be, two different combinations, as we saw before. Else we'd have technically 4 to worry about, which is still feasible. The point is, but x minus y and x plus y have the same parity, because think of it this way. If I have the number 2, if x is 2 and y is 5, 2 minus 5 is negative 3, 2 plus 5 is 7, same parity. You can do this for a lot of things, but it makes sense. You know, you have this, x and y are going to be the same number, and you're subtracting y or adding y to x. So they'll have the same parity. Like 3 plus 2 is 5, 3 minus 2 is 1. They're both odd. 100 plus 50 is 150, 100 minus 50 is 50. Those are both even. But don't overthink it, just understand that's the case. So that's why x minus y equals 2 and x plus y equals 44 is one possibility. X minus y equals 4 and x plus y equals 22 is another. We solve for x and y, and that gives us the solutions. So 23, 21 is a solution, and 39 is a solution. That fits this condition, you know, a solution of the equation in positive integers x and y.